This first table is great, and I'll go over it in class, but in order to save you guys time, I'm going to skip that first table for now. So let's take a look at exponent rules and remind ourselves of exponent rules. Anything to the 0 power is 1. So when I do this problem, I'm going to get rid of that because it's all 1, and we multiply all of this times 1, it's just itself. So 121, x to the 5th, y to the 3rd. Okay, let's jump to the next rule, m to the 1st. Anything to the 1st is just itself, so it's m. So this whole thing to the 1st power is just going to remain the same, 9/5, a to the 3rd, c to the 4th. Next, when we're multiplying and we have exponents, we're going to add the exponents. So if they have the same base, you keep the base and you add the exponents. So 3 to the 2nd times 3 to the 5th times 3 to the -4th, you keep the base 3 and you add the powers. 2 plus 5 is 7, and -4 gets us back to 3. And 3 to the 3rd is 3 times 3 times 3, which is 27. m(a) to the b. That's a power to another power. We actually multiply those. So x, oops, so sorry, that's m to the a. But then we would have x over y to the, and then do the power to the power, so that's 14. Multiply them. Okay, m to the a over m to the b. I mess this one up every time, but when we divide, make sure that we're actually not dividing the exponents. We have to subtract the exponents. So let's do that. X to the 5th divided by x to the 2nd, we're going to subtract and get 2. Y to the 5th divided by y to the 2nd, subtract to get y to the 3rd. Z to the 2nd divided by z, subtract and you get z to the 1st. We'll just leave it like that. And then m to the -a. Remember, anytime you have a negative exponent, you need to move it. So in this case, it's in the numerator. We would have to move that to the denominator to make it a positive exponent. If you were in my class, you would know that. Throw the bad kids in the basement. I won't get into an explanation on that. So when I do 2 minus 4 on this problem with the division, I end up with x to the -2nd. And then 5 minus 5 would be y to the 0, and 2 minus 1 would be z to the 1st. So in simplified form, we cannot have this negative exponent. So I'm going to drop that into the denominator. And then y to the 0 is 1, so 1 times z is just z. So we would have z over, drop that x to the -2nd in as x squared. So pause the video and try to do the problems that say now you try, and hit play when you're ready to see the answers. So I think the most challenging one would be the one that I starred for you. When we have a whole group that has an exponent to it, remember that it's going to each term inside of there, so that would be 2 to the 3rd and a to the 2nd, which is to the 3rd. That's where I got a to the 6th from, but we have to remember to do the 2 to the 3rd as well. So in this section, you're going to be using factor trees. So a factor tree is trying to find the prime numbers that make up the number that we're working with, like 12 in this case. So 12, I'm thinking of any two numbers that multiply to 12. 1 and 12 wouldn't help, but like 2 and 6. So then 2 is prime, circle that, and now I need to break down the 6. What multiplies to 6? 2 times 3. And this can be written out as 2 times 2 times 3, or even better, 2 squared times 3. I'm going to jump to example H. Example H, just because it has variables, it's really not much different. Let's break down 24 first. That would be like 6 and 4. 6 is 3 and 2. 4 is 2 and 2. And now the exponents. We have x, x, and then y to the 3rd. Y, y, y. So that would be 2 to the 3rd times 3 times x times x times y times y times y. Or you could leave that as 2 times 2 times 3 times 3 times x times x times y times y times y. When they're variables, I like to leave it expanded like that so that we can really see what made up, what resulted in the x squared y cubed. I'm going to fill in the rest of these, so feel free to do so as well. I'm just going to pause it in case you want to try it on your own and hit play when you're ready to see the answers. So here are the answers to all of my factor trees. I kept the exponents expanded on the algebraic problems, the variables. So for this next part, I just need you to have seen this one time, but you actually won't be tested on this part if that makes you feel better. So if I'm looking up here, we've got the a root of n would be n to the 1 over a, meaning this exponent is 1 and it becomes that exponent over a. So that's what I'm going to look at right now. So for the square root of n, there's actually a 2 in there. The index is 2. So that would be n to the exponent of 1, so 1 over 2, n to the 1/2. Next, remember it's n, so it's n to the first, so that's going to be n to the 1 over 3. Then it will be n to the 1 over 4. Now for this next one, this is n to the exponent's 2 now, so 2 over 2, which is equal to n to the first, or just n. Okay, and then for this one we have n to the 2 over 3. Okay, so that's that. 2/3 is already simplified, and then here we have n to the 4, that one, over 3, n to the 4/3. So now that you've seen it, maybe you caught on. That's great if you did. Okay, example 1, simplifying square roots now. What we're going to do to simplify square roots is we're going to build a factor tree. So we're going to do the factor tree of 124. So when in doubt, if it's even, divide by 2. So that would be 2 and 62. Then break down 62. It's even again. So 2 and then it's 31. Now there are my prime numbers, which is 2 times 2 times 31. We are looking for a pair of these because remember, we're taking the square root of all of these. Well, if you just look at 2 times 2, the square root of 2 times 2, which is 4, the square root of 4 is 2. So we take that out, take that pair of 2's out as a 2, and the 31 remains inside. So it's 2 radical 31 is how we say that. So this next one, you can multiply these and get 5 times 18 is 90 and then do the square root of 90, but then we need to do a factor tree, which would be like 5 and 18. So if you want, you can just start right here with 5 as the prime number and then do the factor tree of 18, 9 times 2, and 9 is 3 times 3. So I can write that out as 2 times 3 times 3 times 5. Remember, we're taking the square root of all of these. The 3's are my pair. The square root of that is 3, because that's 9, right? Square root of 9 is 3. So the 3 comes out, the pair comes out as one of them, and the remainder gets multiplied inside. 2 times 5, which is 10. So it's 3 radical 10. So if I had multiplied and actually got 90, then I could just, like I said, do my factor tree from there. But it would come out the exact same. Okay, now let's look at it with variables. So let's start with 27. We'll break that down. That's 9 times 3, which is 3 times 3. And then the A is going to be A. The B will just be one of them, and the C. Just write it in a row, or you can write multiply in between all of these. So let's rewrite that. So we have the square root of 3 times 3 times 3 times A times A times A times A times A. I think I need a longer square root here. Times B times C times C. And remember, I can take pairs out. So I could take this pair of 3's out. That's going to be a 3. I see a pair of A's. That can come out. Another pair of A's. And a pair of C's. And what was left inside? Inside we have this 3, an A, and a B, so those will be multiplied inside 3AB. The 3AAC looks weird. Let's rewrite that. So that would be 3, instead of AA, we would write A squared C. And then put that remainder inside, radical 3AB. So we're just looking for the pairs that go outside because we're really taking the square root of them, and the leftovers remain inside.